All right, so when we're dealing with systems of equations, we're going to deal with two variable systems right now. So graphing, you want to graph that on a piece of graph paper, so it's two-dimensional, x and y. But with any system, whether it's 2 variables, 3 variables, 25 variables, it doesn't matter with any system of equations. There are 3 possible outcomes. The most common outcome, and the one we like the best, is when there's one solution. And when there's one solution, if it's 2 lines, if we've got 2 lines crossing, so take, for instance, this red marker or red pen and this pink marker. You know, they're 2 lines, right? If there's one solution, what are those 2 lines going to do on a graph? Are they going to cross or not? One solution? How many places are these 2 lines touching right now? None. But if I do this, how many places are they touching? Once. Okay? So when you have one solution, your graph is going to show that the 2 lines are crossing, or whatever graphs are drawn, they're crossing one solution. So that's, cross at 1 point. The math word that goes with that is consistent and independent. Consistent meaning it's got answers. Independent meaning the 2 lines are going different directions. So they're crossing there. You have a preference for what?
This one is going home with students, so it need to be signed out.
Yeah.
I can do that.
Yeah, just get that number right there.
That number set back to you?
Yeah.
That's right. Thanks, sir.
Yeah. No problem. Okay, so consistent meaning it has a solution. Independent meaning the lines go different directions. They're independent. If you're an independent person, you go your own way, right? That's what makes sense, okay? Second possibility that it could be is that, what was it like when the lines were like this? They didn't touch at all, right? So if crossing is one solution, they touch at one place, what would this be? No solution. They're parallel lines, that's right. That would be a good way to describe it. Parallel lines, if it's lines that we're dealing with. If it's dealing with a absolute value graph, the absolute value graph is a V. It's not, can't be parallel because it's not a straight line. So, but no crossing. Okay. No crossing. And when it's no solution, if consistent means it has a solution, what would the mathy word be for no solution? Inconsistent. Just inconsistent would be the mathy word for that. So tie that together with no solution. Third possibility is the one that's really mind-boggling, is that you could have infinite or infinitely many solutions is how I usually say it. So what would the 2 pens do for infinitely many solutions? Multiple times. So I can't really bend a straight pen. I can't bend this marker, without breaking it. So what would I do, Serena? Yeah, push them together. Can you count how many places that's touching? A bunch. It's everywhere, right? So it's an infinite number of places where it's crossing. So the lines, if it's straight lines, they're going to be on top of one another. Okay, so we'll say that is the same line. Infinite number of crossings. And then when we mix in more complex graphs to this, we'll kind of, that builds as we get more and more different kinds of equations in this class. When you start mixing that together, one solution sometimes looks like, if you got one solution, we're going to get to the point where we're graphing parabolas with straight lines. And then one solution really looks like two places in that case. So that depending on what kind of equations you have, and we'll see that today when we change that parabola to just a V shape with an absolute value graph, there still could be two answers, but it's not an infinite number of answers. There's actually, a countable way of, getting that. So one solution, we say one solution, but we mean, okay, there's a definite place where they cross and you can count those. That's what one solution really means when we get into more complex stuff. This is more or less how you did that with Algebra 1. Now, if there's an infinite number of solutions, the math word for that, it has solutions, so it's going to be what? If there was one solution, we called it consistent and independent. If there's an infinite number of solutions, there's solutions, so it would still be consistent, but dependent. And dependent. And if something is dependent on another, it goes where you go. So they go, the lines go together. So that's where the dependence comes from. Okay, consistent and dependent. All right, so let's look at some examples, graph some lines, and see where they cross or if they cross, and get that review going. Okay, so let's start with 3x plus 2y equals -4, and then 3x plus y equals I'm thinking of it. Okay. Now, if we're going to graph those two lines, what form do we want the equation in? Slope-intercept form. Good job. What is slope-intercept form? Yeah, mx plus b. Okay, so what's the m stand for? Slope. The b is the y-intercept. So we're going to get them in that form, and then we can graph them easily. Okay, we can graph them from this form, but it's not as easy to do. So slope-intercept form is where we're going to go. So let's get the first one in slope-intercept form. What do I do? Subtract 3x. So that's going to be 2y is equal to -3x minus 4. Then what? Divide by 2. So that one in slope-intercept form is y equals -3/2x minus 2. Good to know. The second one, a little easier to get in slope-intercept form because it's just one step, right? You just subtract 3x. You don't have to divide by anything. So it's y equals -3x plus 5. Okay. So these are the two equations that we're going to graph on the same coordinate plane. And hopefully we can find where they cross. I want to show you, hopefully with this, the inconsistencies of graphing by hand and using graphing as a solution. Okay, put your phone away. Take your earbud out of your ear. It's disrespectful. All right, so I'm going to graph the first one, the green one there, that -3/2x minus 2. How do I graph that? Okay, so what's the y-intercept? -2. So I'm putting point at -2, and then how do I count that slope? So -3/2 means we go which direction? Down 3 and right 2. Yeah, down 3, right 2. We could go up 3 and left 2 if we needed to. Be as precise as you can be there. Try to draw that line. Because because we're looking for where these things are crossing. So you want to try to get your line doing as best you can. Okay, straight as you can get it. And then we'll graph the blue in there. Y-intercept for this one would be 5, 1, 2, 3, 4, 5, and a slope of -3 and 3 over 1. So I'm going to just keep going down 3 and over 1 until I get somewhere where it looks like these are going to cross. And maybe I've gotten there. Yeah, I did. All right, so they don't cross at a perfect place. I'm going to try to draw that one a little longer so that we can see where it's at. Down 3 over 2, down 3 over 2. And it's in between some ordered pairs. So we're going to have to do some estimation. Best I can do. So that place right there is where they cross. So we got to guesstimate where that's at. So it looks like, you know, y value wise, it's just a little bit past -9, and the x value would be 1, 2, 3, 4, maybe about 4.2, something like that. The y value would be negative 1, 2, 3, 4, 5, 6, 7, 8.2, something like that. So we're going to have to estimate if it doesn't cross at a nice spot. So 4.2, comma, negative 8.2. That's our solution, our one solution to that. How do I know before I even graph it if there's one solution? What about those equations that are circled there? Tells me that they will cross. Not necessarily the negatives, but we're looking at two lines, two straight, you know, slope-intercept formula lines. What would tell us if they were parallel?
No crossing.
No crossing. That's on the graph, but the equation. What part of the equation? The slope. The slopes are the same on parallel lines. So you know if the slopes are not the same, they're going to cross. Automatically, you know, I got one solution. If the slopes are the same, then you look at the y-intercept. If the y-intercepts are the same, what's that mean? They're infinitely many because they're exact same line, right? You'll see the equations match when they're infinitely many solutions. So you'll see that when we're doing graphing, and we'll see some other ways later on to look at that. So let's look at another one. Let's say we had something like this. Y equals 8x minus 8, and then 2y is equal to negative 3x minus 16. Maybe a little bit better one as far as where they cross on this one. So first one's already in slope-intercept form, so we don't have to do anything to it. What do we have to do the second one? Just divide everybody by 2. Y is negative 3 over 2x minus 8. So I'm good there. I can go ahead and be graphing that. So graph this one red and the other one in blue. So first one, y-intercept is negative 8. 1, 2, 3, 4, 5, 6, 7, 8. Slope of 8. How do you count that? Up 8 over 1. So it's going to go through that point. You go up 8 again. 8 over 1. I usually, get at least 3 points on the first graph, because that usually gets you a little bit straighter of, more accurate line. If you can go from a point way down here to all the way up there, connecting those usually gets you better. Okay, second one, what's the y-intercept? -8. Oh, it's the same y-intercept. That's great. We already know where they're crossing, right? Right there, because they're going to cross how many places? One, because they're straight lines that have different slopes. And I'm going to go ahead and draw that graph, down 3 over 2, up 3, left 2. But I know that they're crossing at that ordered pair. That is the y-intercept right there. That answer would be 0, -8. That's the solution to that. Not incredibly difficult, but same old stuff. All right. Look at this one. Let's say we had y equals absolute value of x plus 1 minus 3. And then y equals x plus 2. So we have an absolute value graph and a linear equation. They're still a system of equations. So that doesn't change what we're looking for. We're looking for, are they going to cross and where? Okay, so let's graph the absolute value graph, because we don't have to do anything to these to get them in slope-intercept form. That one that is in slope-intercept form already, and then the absolute value graph's already set up for us. So on the absolute value graph, what's the vertex? -1, -3. So I'm going to -1, -3. That's my vertex for that one. And then I would count up 1 over 1 in both directions and get that V shape happening. On that absolute value graph. Now the second equation, graph it in red. What's the y-intercept? 2, slope of 1. We got one good place that it's crossing. Does it cross at another place? Why not? Yeah, the one going to the right is the same slope, because this was up 1 over 1. This one was up 1 over 1. So this the right-hand side of the absolute value is parallel to that line. Just happens to be. It doesn't always happen that way. But here we do have a solution. We got a place where it crossed. So here we got one solution. It's possible, what I want you to see on this is it's possible to get 2 solutions with that. Because if your line just had a different slope, it's going to run into the other side too. But here, the only solution we have is that one, and that's at what point? -3, -1. So there's the solution to this one. Mixing in what we did last couple of days with what we're doing now. Always a wonderful thing. Let's say we had 2x plus y equals 4, and then 4x plus 2y equals 3. So 2 linear equations again. Got to get them in slope-intercept form, right? This one, subtract 2x. You got -2x plus 4. That's good. Next one, subtract 4x divide by 2. What's happening here? Got 2 equations. What do we know about them? What are those? Same slope. Y-intercepts are different, right? So that means these 2 lines are what? Parallel. Are they going to cross?
No.
No. Is there any point in graphing that? No. You know they're not going to cross. So what's graphing it going to show you? So this would be no solution. You could put the circle with a slash through it. If you want to use that symbol, that's fine. It stands for the empty set. It means there's no answers, no solution. Now, if you had the same slope and the same y-intercept, what's that mean? Infinitely many solutions. Okay, so look at your equations. If they're the same slope, check the y-intercepts. If they're the same, it's infinitely many. If they're different, no solution. You don't even have to graph those. The only ones you're really going to have to graph are the ones that you know are going to cross somewhere. Okay, so if you know they're not going to cross, or you know that they lie right on top of one another, there's no point in graphing those. Okay, all right. Let's hop over to section 3.3 and talk about some inequalities. Won't take us very long to do this because we've already talked about all the review stuff for graphing lines. Inequalities is a quick review too. So section 3.3, systems of inequalities. And with systems of inequalities, you know, with equations, there are other ways to solve them other than graphing and produce an answer. With inequalities, really the graph is the answer, because with a system of inequalities, there's going to be an infinite number of solutions. If there are any solutions, there's going to be an infinite number because it's a overlapping of shading type thing. So when you're looking at graphing a system of equations, and we'll just pick up with that, y is greater than negative 2x minus 5. We'll use that one. And then y is less than or equal to x plus 3. A couple of simple ones to start off with. And you're going to graph those two on the same coordinate plane. So we'll review as we work here. So when I go to graph the top one, what do I have to remember? I'm going to graph that with the red pen. What's different about it than graphing an equation? Well, yeah, it's got a symbol, and the greater than symbol instead of the equal to symbol. So we do the y-intercept the exact same way and the slope the exact same way. That's where it changes after that. So we'll go to negative 5, 1, 2, 3, 4, 5, down 2 over 1, up 2 left 1. Do that a few times. Now, here's where it changes. Instead of just drawing a straight line through that, you've got to think, okay, what kind of symbol did it have? It had a greater than symbol. So that means we're going to use what kind of line? I remember that from Algebra 1, maybe. This is one of those things you probably didn't do in geometry, so you didn't catch any review there for this. So.
Is it like the dotted line?
Perfect. Yes, it's a dotted line. Why is it a dotted line and not a solid line? It's greater than. It doesn't have the equal to mark. If it's the equal sign or the equal to mark, it's a solid line. So we're going to use a dotted line to do that. So dotted. Then it's still different. We're not done yet because we need to shade one side of that line. And various ways to do this or decide that. I always like to use a test point. So if you had me for Algebra 1, you remember doing a test point, or hopefully you remember doing a test point. And that means you pick a point that's on one side of the line. So I'm going to pick the origin if at all possible, because 0, 0 is the easiest math that I know how to do. I can plug zeros in and do the math pretty quickly. So if I plug 0, 0, it's on the right-hand side of that line. I'm going to plug it in here, 0 for y and 0 for x. So when I work that out, the negative 2x goes away, right? So it's 0 greater than negative 5. Is 0 bigger than negative 5? Yes. Because $0 is better than owing somebody $5, right? So 0 is greater than negative 5. So that means it's true over here with 0, 0. So I'm going to shade that side of the line. If it were false, I would shade the other side. So true side, it's true. I'm going to shade that side. I'm going to shade with some yellow highlight here. Just lightly shade that with your pencil. I don't have a choice. It's on or off here with the pen. So just lightly shade that because you're looking for an overlap and you want to be able to still see your grid so you can graph the other line. Okay. So graphing the other line, y-intercept is what? 3, slopes 1. That's easy. I can do that. I'm not really concerned about the exact point that they cross at. That's not important right now. We'll get to some stuff later on this semester that it is important, but right now it's not. We're just looking for some shading happening. I used a solid line. Why did I use a solid line? Yeah, because it had an equal to mark on it. Okay. Then it says less than. Some people teach, if it's less than, you shade below that. But as that line gets more vertical, below gets more blurry. What's below if the line's real vertical? Yeah. All right. And then, so I always do a test point. So I'm going to check the origin again because the line's not going through it. So if the line's going through it, I can't use the origin. So I can on this one. 0 less than or equal to 3. Is that true? Yeah. So that means I want to shade the side that 0, 0's on because that's true.
May I have your attention, please? At this time, of these seniors with the last name of L through Z. You have your deposit and order forms for Johnson to report to the front lobby close to the cafeteria. Thank you.
That area that overlapped into green, is there anybody that's colorblind in here? So I use colors a lot, and if you're colorblind, it doesn't really mean anything to you. I don't ever think about that until it's after. This green area where they overlap, that's the solution area. That means any ordered pair in that green area is an answer to this system of inequalities. Okay, so there's an infinite number over there. This keeps going on forever. If you extended the graph, it'd be huge. But there's a ton, like an infinite number of ordered pairs that are solutions to that. Okay. So that solution area there on your paper, the darkest region that's on your graph. If it's hard to tell, point me an arrow to it and write solution area, something like that. Just let me know where the solution area is. That's what I'm looking for there. Okay. Let's do this one. Y is less than or equal to 3, and y is greater than absolute value of x plus 4 minus 2. Both of those already have y by themselves. So that means I don't have to do any preliminary work to get them ready to graph. But I do have to remember something about y equaling a number and what that graph looks like. Anybody remember what that graph of y equals 3 would be?
It would just be a flat line
Yes.
at 3.
Yeah, a flat line or a horizontal line at 3. So I'm going to go up here to 3 on the y-axis. Just draw a horizontal line. Should it be a solid line or a dotted line? Why solid? Equal to mark says solid. Okay. Bottom one, it's absolute value graph. Oh, wait, I hadn't shaded the top one yet. Let's do the shading first. We're getting in a hurry. Shading on the top. Less than 3. Can I check 0, 0? Yeah, there's not an X to plug in for, but I can check the 0 Y value. Is 0 less than 3? Yeah, so I'm going to shade below that line. The less than kind of helps you, say below that line. On the horizontals, that's easy to look at and say, oh, it's less than, I'm going below it. So I'm going to shade below that line. All right. And then let's go graph the next one. Vertex of that absolute value graph. -4, -2. Yeah, got to get that opposite of that in there. So -4, -2. So that point right there. And then the slopes, which way is this going to open? Up or down? Up, because what's in front? Just a 1, a positive 1. So it's going to open up 1 over 1. Both directions. Dotted or solid? Dotted. Good, Gage. Yeah. So make it clear that it's dotted. If it's hard to tell because of your shading, point to it with an arrow and say this is a dotted line, so that I make sure that I know what you're trying to tell me. So then shading. Absolute value graph, you're either going to shade inside of the V or outside of the V. Okay, so I can check a point that's outside of the V, and if it's true, I'll shade outside. If it's false, I'll shade on the inside. So 0, 0, perfect choice because it's easy math. So 0 plus 4 is 4. What's the absolute value of 4? 4. 4 minus 2 is 2. Is 0 bigger than 2? No, that's false. So that means I'm going to shade on the inside of the V. So that little triangle there is the solution area. Awesome. Do another one here. X is greater than or equal to 5. Y is less than -3. Trying to get some of these that we oftentimes forget how to graph them when we're doing this stuff. So both of them have the variable by themselves, so I think they're ready to graph because I don't have to do any work. That's a good thing. We'll start with the one we know, hopefully, because we just did one like it. Y is less than -3. What's that look like? Horizontal line, right? At what? On the y-axis. So dotted or a solid horizontal line? Dotted, yeah, be careful. That says only equal to's are solids. Okay, that's good. So be careful of that. That's an easy thing. It could cost you a couple points here and there. Or it might cost you the whole thing, okay? Less than that's going to go above it or below it? Below. Shading below that. Okay, now the graph of x and a number. What's it look like? Vertical line at on the x-axis. 1, 2, 3, 4, 5. Should this one be solid or dotted? Solid. Because it has the equal to mark. So here we have the horizontal line. Y and a number is going to be horizontal. X and a number is going to be vertical. And then we need to graph the shading for this. So X is greater than 5. So where would greater than 5 be? Be that way, right? To the right. So we're going to shade to the right of that vertical line. Screw that up. Solution area is that little box down in the corner. And And I'm just trying to indicate that for us to know that that's where all the solutions are. Not too bad though, right? Pretty easy stuff. Let's do one more and we'll be done for today. I won't bother you. So move on. Let's say we had negative 4y is greater than x. And then y is greater than or equal to negative 2 absolute value of x minus 3 plus 4. It's a little bit more fun. So the first one doesn't have y by itself. It's got y and x in it, so I need to get y by itself. How do I do that? Yeah, divide by negative 4. Good. But when I divide by negative 4, what happens? I get a fraction, negative 1/4 x. What else happens? Symbol changes. Remember, if you multiply or divide by a negative with an inequality, it flips it around, flips that symbol. And that's one of those small things that makes a big difference, because that's the difference in shading above a line or below a line, whether it's greater than or less than. So be careful of that when you got to get y by itself. Make sure if you multiply or divide by a negative, then you've got to flip that symbol. Okay. All right. So we got that one good to go. The second one's already in the right form. It's in that absolute value vertex form type thing. So we're good with that. So let's graph those and see what happens. That's the spot. All right. So I'm going to graph the top one. What's the y-intercept for negative 1/4 x? 0. So that's the origin. And I'm going down 1 over 4. And up 1 left 4. Do that a couple of times. Is that a dotted or a solid line? Dotted, yeah. Dotted line. Now, I've got to shade that, and I can't use 0, 0. Why can I not use the origin? Because the line's on it, okay? Or it's on the line. So I can't use that. I got to pick some other ordered pair to check. So I'm going to pick something easy like 1, 1. That's what is 1 less than negative 1/4. Positive 1 less than negative 1/4. No, so it's false over here. So that means I'm going to shade this half, the bottom half. Also think less than, lower than. So underneath that line. That's one way. That's another way to do it. I won't say that the way I do it is the only way, because it's not. It's just the way I feel most comfortable with. All right. Now let's graph that absolute value graph. Blue. What's the vertex? Positive 3, 4. So I'm going to go to 3, 4. Which way is it going to open? Down or up? Down? A couple of people say down. So down, and we're going to count how? Down 2, right 1. Down 2, left 1. Down 2, left 1. Down 2, right 1. Do that a few times. That shape. Dotted or solid? Solid. That's equal to mark. So we can go solid. Okay. Shading. Ooh. Can I check with the origin on this one? Yeah, that's a good spot, because it doesn't go through it. The red line goes through it. The blue one doesn't. So I'll put a 0 in here. So 0 minus 3, negative 3, absolute value of negative 3. 3 times negative 2, negative 6 plus 4, negative 2. Is 0 bigger than negative 2? Yes. So that means I'm going to shade where the origin is at. So that's on the outside of the V. Shading the outside of that V. We got a couple of areas of solutions. That's interesting. So you got solutions, and there's another solution area. Two solution areas showing up on this one because they're separated by this area that's not a solution on the inside of that V. A little bit more complex graphs than what you did in Algebra 1. Still a lot of the similar, concept. Nothing really changing about that. Okay. Questions about systems of equations by graphing or systems of inequalities by graphing. Okay, so assignment that you can work on today if you want to go ahead and start on it. It's not something you have to do today. You'll have a work day tomorrow, but you can start on it today if you want to. Page 156, 3 through 14, 17 through 28, 35, and 36. Page 171, 5 through 25, and we'll just do the odd ones on that page. Do all on that page. Okay, so that's going to be our assignment for today's stuff. You got about 14 minutes left in class today, and then you'll have class time tomorrow to work on this, ask questions, get all that stuff done. Homework from yesterday